Um, Today's speaker is Matt Long from NCAR, who's going to talk about the atmospheric signature of Southern Ocean carbon flux. I'm really pleased that you're willing to present this today, Matt, and I'll let you take it away.
Great. Thanks, Sarah. Thanks for the introduction. I'm happy to be here. Happy to tell you guys a little bit about this story we've put together over the past few years based on aircraft and surface atmosphere CO2 measurements. So a starting point for this is, probably pretty common knowledge amongst this crowd, but basically here's a figure illustrating the fluxes and the global carbon budget, demonstrating that, of the annual CO2 emitted, of the CO2 emitted annually by humans, about half is taken up by the terrestrial biosphere, and about a quarter is taken up by the terrestrial biosphere, and another quarter is taken up by the ocean. And the function then of these natural sinks is critical to the trajectory of the climate system. Here's a figure from a recent paper from the Global Carbon Project showing the evolution of the ocean carbon sink and the spread basically between surface ocean PCO2 observations used to constrain global interseas flux and the collection of global biogeochemical models. And this just demonstrates that that there's significant uncertainty that persists despite significant advances over the past few decades in our understanding of interseas CO2 flux. The Southern Ocean happens to be sort of an outstanding area of interest, and here's a figure from a compilation of CMIT-5 models showing the seasonal evolution of air-sea flux in the region south of 44 South, along with an observational or two observationally based estimates. This dashed line is the frequently used Takahashi 2009 climatology. But this just illustrates the degree to which the system is challenging to model in the Earth system modeling framework. One of the reasons for that is because the net CO2 flux across the air-sea interface manifests as a result of strong opposing terms, and I'm illustrating that here, breaking down this observationally based net flux, the blue line, into the seasonal component driven by thermal forcing, so just changes in the sea surface temperature, and the non-thermal residual, which is comprised of the surface DIC tendency attributable to biology and vertical exchange. And as a result of basically these strong opposing terms, the net flux is relatively weak in magnitude, but slight offsets in a model between the phase of these opposing terms can yield large changes in the phase of the residual. That was illustrated nicely here in a paper by Jiang et al., looking at PCO2 observations in the Drake Passage in the same collection of CMIT-5 models showing the observations, now in PCO2 non-flux space, and the degree to which the models disagree on the phase and amplitude of that variability. Notably, they demonstrate significantly better correspondence in the thermal component, and the degree to which their discrepancy in the total is evident largely in the non-thermal term, though both components contribute. Another sort of issue with the Southern Ocean is that the large-scale overturning circulation brings water that is rich in DIC to the surface. A portion of that DIC outgasses before that water is then subducted back into the interior. And so there's another cancellation at play here, which is the natural outgassing of CO2 compensated by the uptake of anthropogenic CO2. This region is critical for us to get right in our models and to develop a sound observational assessment of the flux, in part because it contributes significantly to the global carbon budget. Here's a picture showing the column inventory of anthropogenic CO2 circa mid-1990s. And about 40% of this anthropogenic inventory entered the ocean through the air-sea interface in the Southern Ocean. So this is an important area to advance our understanding. As we move forward and society begins to engage in mitigation, it's going to be increasingly important for the scientific community to be able to provide clear and accurate assessments of the state of the natural carbon cycle so that we can provide unequivocal explanations for the trajectory of atmospheric CO2, a critical underpinning for the viability of agreements such as the Paris Accord to mitigate CO2 emissions. So some of that backdrop was the motivation for the ORCA's field campaign. This was a campaign that Britt Stevens and I, a colleague of mine at NCAR, co-led in January and February of 2016, aboard the NSF NCAR Gulfstream 5 aircraft, both based in Punta Arenas, Chile. We flew 19 research flights from Punta Arenas that are illustrated by this figure at the bottom of the slide here. Notably, this is a picture of Elephant Island taken out of the window of the G5 in early 2016. This picture was featured on the cover of BAMS in association with a summary paper we published describing the field campaign. Notably, this was almost 100 years, not quite to the day, but almost exactly 100 years after Ernest Shackleton's crew decamped from the Wet Sea, where their ship was being crushed by ice. They escaped on their lifeboats, headed north and landed on Elephant Island. Subsequently, a small group of them, they hardened down one of the lifeboats, and subsequently a small group of them sailed that lifeboat north to South Georgia Island to a whaling camp where they were where they basically enabled a full rescue of the whole crew. Interestingly, I don't know if people saw this in the news this week, but just 2 days ago, it was announced that Shackleton's ship was found in the Weddell Sea, and this is a picture taken from a drone that was sent down to video that ship. And it's just amazing to watch this footage of the ship that is just nearly perfectly preserved at the bottom of the Weddell Sea. Well, that was an aside. Our mode of transportation 100 years later was a bit different. Here is a picture of the G5 off the Western Antarctic Peninsula taken by Alex Chin, who was aboard the RV, the Gould, US icebreaker ship. And you can see in this picture a couple things. One is that there's these sort of bristles sticking up out of the plane, and those are inlets for gas sampling. So the plane itself is kind of the instrument that's flying around, sniffing atmosphere as it goes. And here's what it looks like inside the plane. There's Ian McCubbin sitting at a rack that has the portable remote imaging spectrometer, hyperspectral, downward-looking ocean color sensor, and Britt Stevens squeezing his way between two racks here. Key instrumentation for the purposes of this talk are the airborne oxygen instrument, which is developed by Britt at NCAR, capable of measuring the O2-N2 ratio in real time as the plane flies, and the Picaro quantum cascade laser spectrometer, the Picaro ring down cavity spectrometer, a laser-based measurement, spectroscopy measurement capable of measuring very high precision CO2, methane, and water. Just to give you a sense for what this is like and how the observations are collected, I'm going to show you this video from a research flight. This is our third research flight. The map in the upper right shows the location of the plane. We took off from Punta Arenas. The bottom right figure here shows the altitude of the plane in gray. And then there's two traces. In red is the oxygen anomaly, or the O2-N2 ratio in per meg, and the CO2 concentration in blue. And so we took off from Punta Arenas. We climbed to about 41,000 feet, took a dip to measure the properties across the top of the troposphere, and then back to fuel efficient cruising altitude as we transited south. We approached this location near the sea ice margin off the coast of the Western Antarctic Peninsula, and then begin conducting a set of profiling dips to measure properties across the top of the planetary boundary layer. And so these descents and ascents are basically, the plane is going to about 500 feet above the ocean surface. And if you look closely, you can see some seals sitting on ice floes and other animals. And then it climbs up to about 3,000 feet or so, and then dives back down. So that was one measurement objective on the ORCAS campaign, which is to capture these sort of regional scale gradients that manifest in changes in properties across the top of the boundary layer. A second measurement objective was to capture the large scale structure of CO2 and oxygen in the full troposphere to enable inferences about flux processes on the full hemispheric scale. So after we finished our boundary layer dips, we headed north and conduct a series of profiling observations across the full, across a large portion of the troposphere. So from the ocean, near the ocean surface up to about 28,000 feet. One of the things that you can notice in the context of these dips is that as the plane descends, there is an anti-correlation in the boundary layer where oxygen tends to be elevated when the plane is near the surface and depleted aloft, indicative of, and CO2 has the opposite behavior, indicative of strong biological activity in the surface ocean. Okay, so that was the measurement campaign. Here's what the sort of full picture of those gas fields might look like, represented in the context of a full Earth system model. So this is an integration of the community Earth system model, which we coordinate the development of here at NCAR. And what I'm showing you is the daily evolution of oxygen and CO2 anomalies in at the surface and then across a zonal section. There's some funny stuff happening in the up in the stratosphere of the model, which is basically just indicative of time lags and insufficient spin up. But what you see in the context of the tropospheric inventory and the structure of these tracers at the surface is indicative of what the plane was sampling. And so you see this accumulation of oxygen in the summer hemisphere. Now at this point, we're just reaching summer in the northern hemisphere. And so we see oxygen begin to accumulate associated with the depletion of CO2. I should say that these tracers are only responsive to surface fluxes, so ocean fluxes. So I've taken out the land and fossil component here. Coupled with that sort of seasonal evolution is this synoptic variability as these sort of large scale gradients are stirred by synoptic systems, storms passing through. Okay, so collectively aggregating all the measurements that were taken of CO2 on ORCAS yields a picture that looks something like this. This is an altitude latitude cross section where we see this strong depletion of CO2 at the near surface in the high latitude southern hemisphere, accompanied by enhancements of CO2 likely attributable to long range transport from the northern hemisphere aloft. And this is again the picture of the research flights that we conducted on this campaign. So some initial results from this campaign taken from our BAMS overview study are represented here. These are the profiles of oxygen, of CO2, and then flavors of CO2 as inferred from the model in profile view aggregated across all these measurements. And so what we see is this enhancement of oxygen in the lower troposphere coupled with the depletion of CO2. The Earth system model does a fairly good job of getting both the structure and the magnitude of these gradients correct, though it kind of overcooks the oxygen enhancement in the lower troposphere, perhaps indicative of having both thermal and biological forcing that is too strong. I instrumented the model with air mass tracers that, well, actually, these are just CO2 tracers. And so what we can see is that the signal in the vertical gradient here is primarily attributable to the ocean, with a small contribution from fossil fuel. So these gradients manifest as the convolution of surface flux patterns with transport. And so what this suggests is that these drawdown signals in CO2 are predominantly attributable to ocean fluxes. Here is a scatter plot showing the relationship between oxygen in the troposphere and CO2 concentrations. And what we see is that there's a strong negative relationship indicative of the fact that biological drivers are dominant in driving the surface flux. Here's some results from a paper that Eric Morgan published a couple of years ago on these data. So the ORCA's campaign research flights here. We ran transport model integrations to compute backward trajectories for these measurement locations. And these are the backward trajectories of receptors at the top of the planetary boundary there. And so you can sort of see where the air mass last outcropped at the where the air mass was the footprint of the air mass at the surface. So these boundary layer gradients are predominantly indicative of signals aggregated over these relatively modest regional scales. What Eric did in this analysis was basically to compute differences between CO2 in the boundary layer and CO2 above the boundary layer, and define those as metrics delta CO2, delta O2, and then the gradient, which is the ratio of those two difference metrics. And so what we see is that CO2 tends to be depleted, oxygen tends to be enhanced, and the gradient is negative, consistent with this biological influence. There's also an indication of sort of a reduction in the magnitude of that gradient as the season or the aircraft campaign in the season progresses. Okay, I'd like to turn now to some results we published late last year in Science on using the aircraft observations to develop quantitative estimates of the RC flux. So a starting point for that is this collection of, or a collection of atmospheric inversion models. So the inverse problem basically uses the flow that's simulated by a GCM as a linear operator to translate fluxes over some region of influence to a simulated concentration in the atmospheric interior. And then because we have a network of atmospheric observations of CO2, those models can be optimized, or the fluxes driving those models can be optimized to develop inverse flux estimates. So here is a collection of the seasonal evolution of flux estimates derived from a handful of inversion model systems. CT is the carbon tracker system developed at NOAA. We have two versions of that system, 2017, 2019B. Carbon Tracker Europe, the Japanese, MIROC, ACTM, and CAMS developed in France. And what you can see here is that there's a diversity of behavior, and the inversion systems have not converged on a consistent estimate of the flux. The Carbon Tracker Europe has virtually no seasonality in this Southern Ocean flux. I should say this is the region south of 45 south. Carbon Tracker Europe has virtually no seasonality, while the Carbon Tracker, the US Carbon Tracker model has perhaps the most pronounced seasonal cycle. So the diversity of these flux estimates manifests from differences in the assumptions related to how close the inversion, or how far the inversion is allowed to wander from its prior flux estimate, typically derived from surface ocean PCO2 observations, as well as many other assumptions that go into this. But a significant component involves the transport uncertainty, particularly in the schemes mediating boundary layer ventilation processes, and the fact that surface observations of CO2 in the Southern Ocean are relatively sparse, and these are global systems that have to meet tighter constraints elsewhere. So another approach to developing air sea flux estimates from observations is one that was clearly pioneered by Taro Takahashi over the years of his career. And I'm pulling some figures here from his 2009 paper showing sort of the density of surface observations that he was using, as well as a global estimate of the air sea flux he derived using basically this equation. And so the notion here is that if you measure the PCO2 at the ocean surface and you have some understanding of the atmospheric PCO2, then with an estimate, with a wind speed dependent transfer velocity and the thermodynamics constraining CO2 solubility, you can develop an estimate of the flux. Well, this approach is fundamentally limited in the Southern Ocean. Did I skip something? No, this approach is fundamentally limited in the Southern Ocean, particularly in winter, by the sparsity of surface ocean observations of PCO2. So I've now just taken the figure I showed you previously with the collection of inversion models and added some estimates of the flux based on surface PCO2. So those include these orange lines, which are Christian Rodenbeck's mixed layer PCO2 assimilation scheme, as well as a compilation of the SOCAT PCO2 data developed by Peter Landschutzer using a neural network algorithm for extrapolation. Okay, so even in these products, depending on the methodology, there's a diversity of behavior pretty much across all seasons. Well, that's sort of the state of the affairs until the Socom project came along, deploying a bunch of Argo floats instrumented with pH sensors, from which the Socom project has basically devised a means to estimate surface PCO2 from the pH observation. Okay, so here's the state of affairs with respect to the seasonal evolution of flux in the Southern Ocean prior to Socom. And here are 3 Socom-derived estimates of the seasonality of flux in now beige. These are developed by Seth Bushinsky and colleagues in a 2019 paper. The pentagons here are basically taking the SOCAT data and adding the float-based estimates. And so what you see is that the wintertime outgassing with inclusion of the floats gets more intense, and the summer uptake changes only moderately. But then Seth also included a couple of sensitivity studies. The squares are just excluding the use of SOCAT in the region where Socom floats were active. And what that does is yield a much stronger wintertime outgassing and a significantly weaker summertime uptake. And then thinking that there might be a potential bias in the floats, they subtracted 4 microatmospheres from the PCO2 estimate and developed this third sensitivity flux estimate, which is shown in these small dots. Okay, so this is sort of the state of affairs with respect to our ability to estimate seasonal fluxes. So I'll just walk you through our approach, which leverages the type of observations that we collected on orcas that I showed you previously. So here's the orcas campaign where we started in Boulder, had a transit flight south, and then conducted several research flights out of Punta Arenas. A previous campaign, Hippo, did pole-to-pole transects on the NCAR G5 in the Pacific, and then a subsequent campaign, ATOM, did a similar thing to Hippo, but also flew up the Atlantic. And both these additional campaigns had observations in the Southern Ocean. And so we're able to basically compile a collection of transects across several months of the year from the composite of these 3 aircraft campaigns. And so this is what that looks like when you aggregate up the CO2 sections. Here are the data from orcas in January, February of 2016. And then you can see that similar structure is evident in the other aircraft campaigns. If we look at sort of the winter months, well, what we see, or summer to winter, what we see is this intense drawdown evident both in Hippo, or in all three Hippo, Orcas, and ATOM. As we move into to fall and into winter, you can see that the nature of that drawdown becomes much less intense, and there's a more homogeneous distribution. Another resource available to us from the perspective of the atmosphere is these surface monitoring stations, which have several decades worth of data available. This is just showing the temporal coverage of data going back to about 1999 from several monitoring stations over the Southern Ocean. And those data look kind of like this. There's strong seasonality. I've overlaid now the location of these stations on a surface atmosphere field simulated by CSM that shows this annulus of low CO2 air surrounding Antarctica in summer. This seasonality is obviously superimposed on a strong trend attributable to the fossil fuel emissions. And also, just to give you kind of a sense of what this is like, the seasonal cycle at Mauna Loa is something like 8 ppm, and here we're dealing with a much, much smaller signal, which is about 6 months out of phase with the Mauna Loa record. Okay, so to devise flux estimates from these observations, what I've done is define 2 gradient metrics. The first is delta theta CO2. That's what I'll call a vertical gradient metric, though I've defined it on the basis of potential temperature coordinates. And it is just the value of CO2 measured below 280 Kelvin isotrope, minus that measured in this sort of mid to upper troposphere range, 295 to 305 Kelvin. Similarly, a horizontal metric, delta Y CO2, is the value of CO2 measured in stations that are located in the center of that annulus of low CO2 air, summertime low CO2 air. So I've just called those Southern Ocean stations. So the average of those Southern Ocean stations minus the value of CO2 at South Pole. So the objective of using these gradient metrics is to be able to filter out external influences like the long-term trend associated with fossil fuel, and basically isolate a component of the local structure in CO2 that is attributable to processes occurring locally, specifically the air-sea flux. So here's sort of a summary of the data assets that we have. Here is a summertime section collected on orcas, I've shown you this picture now a couple times, and a comparable section in winter from ATOM. You see this strong, intense drawdown in summer, followed by more neutral conditions in winter. And then here is an assessment of the spatial structure in the delta Y CO2, the horizontal gradient. So, because SPO is our South Pole is our reference, that's about 0. See this low CO2 air over the Southern Ocean in summer, followed by these weak enhancements in winter. We can look at these data now in a more explicit seasonality, in a more explicit seasonal sense. And so here is a composition of the vertical profile of something like the delta theta CO2 metric, where again, there's strong drawdown in the lower atmosphere in summer, followed by more homogeneous conditions in the other season. And here is the value of this delta theta CO2 metric collected on each individual research flight across all of these campaigns in the small dots, and then as well as the flight median in the large symbols. And so what you see is that conditions are relatively neutral in seasons other than summer, where this strong lower troposphere drawdown develops. Here's that same plot again, the delta theta CO2 metric. And then here's the seasonal evolution of the horizontal gradient across this collection of stations. The key thing to note here is that the magnitude of this signal in about 2.5 ppm is roughly a third of that in the vertical gradient. And so given signal to noise ratios associated with measurement precision, the degree to which these station observations are maintained by different laboratories that have limited intercalibration efforts, this is a small signal relative to the noise. Okay, so in the context of this analysis, I've leveraged this large collection of inverse models and sampled each of the models like the observations. And fortunately, the models all represent the different flavors of CO2. So tracers responsive only to surface, land, and ocean fluxes, respectively. Here is the median signal of these gradient metrics represented by the models. A key question is whether these gradient metrics are responsive to the processes of interest, specifically Southern Ocean fluxes. And here is an indication that they are, because the seasonal structures, the seasonal variability in the gradient metric computed on land or fossil CO2 tracers shows very limited structure. Fossil CO2 here in red contributes something to the annual mean negativity of this gradient, but with limited seasonality. And the case is similar for the horizontal metric. Indeed, if we look at the ocean tracer directly, we see that these gradients are responding specifically to ocean fluxes, ocean processes. So at the core of our ability to develop quantitative estimates of air-sea flux from these observations is something akin to what we might call an emergent constraint, though the conceptual definition is slightly different from its typical usage in the literature. But the basic principle is that we plot the quantity, something we want to know, the air-sea flux south of 40, against something we can develop an observational constraint on, in this case, the vertical gradient in CO2. And what we find is that when we sample this collection of inverse models, like the observations, and compute this vertical gradient metric, and plot that vertical gradient metric against the flux that occurred in the region of influence for the 90 days prior to the development, to the observation, we get a fairly tight linear relationship. And that provides the means then to estimate fluxes. And so here, for instance, for example, is the vertical gradient we measured in January on orcas, which implies, the intersection of this line with the y-axis provides an estimate of the expected value of the flux. So we've done this basically for summer. That's the plot I just showed you, as well as winter, because the relationship between the gradient metric and the flux changes as a function of atmospheric transport phenomena, specifically vertical stability, and that changes as a function of the seasons. What we found is that largely anything but summer could be lumped together into one relationship. Similarly, here is the gradient, flux gradient relationships developed from the surface observations. So this is now the horizontal, the flux versus the horizontal gradient. What we see is there's a relatively robust relationship in summer, but no significant relationship in winter, indicating that the surface station network is really not sensitive to the variation in wintertime air-sea fluxes. Okay, putting those data together along with the flux, seasonal evolution of flux that I've shown you previously, here is now the aircraft-based estimate of the seasonal evolution of air-sea flux in black. So along with uncertainty associated both with analytical precision and the statistics of applying this fit and developing an estimate of the flux. And so each of these black dots corresponds to one of the aircraft campaigns. And what we see is that this evolution suggests an estimate of the flux that's really actually agrees quite well with the Socom data with respect to the phase and amplitude of the seasonal variability, but it suggests significantly less outgassing and more significant summertime uptake than the float data would suggest. By virtue of fitting a harmonic function to these points, I am able to use the parameters of that function to develop an estimate of the annual mean flux, and the number we get is about half a petagram of uptake. Just for comparison, that's nominally consistent with the mean of the inversions over different averaging periods, the mean of the SOCAP-based neural network extrapolation PCO2 flux estimates over different averaging periods. But it is not consistent with this with the estimates derived from the Socom floats. So this is indicative perhaps of an issue with the Socom floats that's generating a bias in those flux estimates. While the signal to noise ratio and is of the surface data is not favorable, those data do offer the potential to look at these properties over the course of several years, in this case, a couple decades. And this is the image we see. So on the top row of plots here, I'm plotting this gradient metric directly, the black line showing the station average. And what you can see is that there is an apparent intensification of this gradient, a statistically significant trend from about 2005 onward, where the magnitude of that gradient is increasing. Because there was no relationship between the gradient and the fluxes in winter, we can't develop a quantitative estimate of the fluxes for winter time, but we can do so for summer. And I've done that for pentadal time periods from the surface data indicated by these dashed lines with associated uncertainty. And so while the uncertainty is large, there is broad agreement. These colored lines are fluxes from the inversions. There's broad agreement between the surface data and the fluxes that we obtained from the aircraft, and an indication of an increasing flux, which would be something that we'd expect on the basis of rising atmospheric CO2. Okay, so just a quick summary of these results here before I turn to a few other sort of future work and other points and wrap up. So the aircraft observations we find provide robust estimates of the constraints on air-sea CO2 flux in the Southern Ocean. The flux number we get is about a half petagram. The surface network is not sensitive to the fluxes in the winter, but despite the uncertainty, indicates trends that are consistent with increasing uptake over the past 2 decades. And the phase and amplitude of the float-based flux estimates are consistent with our findings, which suggests that there may be some uniform sign bias or something that needs to be addressed in the methodology used to derive fluxes from the floats. I'd just like to point out here that I've been kind of an advocate for reproducible science, and I'm trying to put my money where my mouth is. And in support of this paper, we published a Jupyter book that contains all the code and instructions for reproducing this calculation. This required a fair bit of effort, and is something that I look forward to improving my capacity to do in the future. I also want to highlight a few results from a collaboration with Magdalena Carenza, who was a postdoc at NCAR, and came to NCAR with the interest of exploring the role of synoptic weather systems, storms, specifically in the Southern Ocean, in driving air-sea flux anomalies. And so here are some results from a paper she's putting together describing the role of storms in driving air-sea flux. The figure in the top left here is a composite image of storm-associated flux anomalies computed from a CESM ocean ice integration. And what you see is that there is this tendency for storms, low pressure systems in the atmosphere to drive outgassing, kind of in a pattern that's slightly offset from the center of the low pressure system. And here is what the temporal evolution of that signal looks like. This strong outgassing anomaly co-located in time with the passage of the cyclone event. And then a projection of the role of these CO2 anomalies attributable to storms spatially. Notably, in the model, we've tracked down that the dominant factor driving the storm-related air-sea flux anomaly is the drop in atmospheric pressure that is used to compute the partial pressure of CO2 in the atmosphere. And because of the way we forced the model with a uniform atmospheric CO2 field, but time varying, spatially varying pressure, there's a degree to which this simulation is not fully realistic, but this drop in pressure basically, visualized here generates a reduction in atmospheric CO2 because atmospheric CO2 is computed as a function of the mixing ratio times the atmospheric pressure, and then leads to this outgassing. While the response in PCO2 itself, shown in blue here, is relatively modest in the model. Magdalena has actually compiled the PCO2 or the pH-based PCO2 estimates and associated flux estimates derived from the Socom float data, and sees a picture that's nominally consistent in at least the sign with respect to the model, showing that that aggregating float-based flux estimates in storm-centric coordinates indicates this storm-associated outgassing. Somewhat noisy in this view, but there's a clear temporal signal in the flux anomaly. But the floats seem to suggest a stronger amplitude of surface ocean PCO2 variability that is indicated by the model. And we're still working on the interpretation of this, but I think that there's some interesting things to think about here in the context of model validation around structures of variability, such as storms, which provide sort of canonical things that the models should, canonical phenomenology that the model should be able to reproduce. Finally, I just want to talk a little bit about future work. And so several years ago, Britt and I wrote a proposal to put a Picaro CO2 analyzer on a platform of opportunity, which is the US Air Force, the Air National Guard C-130 aircraft that service McMurdo Station and South Pole during the time that the ice runways get too slushy for the C-17 aircraft. And so these are skied aircraft that are capable of landing on the ice sheet. So the idea of this project, which was actually supported, but has been sort of in a COVID-related holding pattern, is to fly repeat transects on these C-130s. Hopefully the scientific staff who are flying between Christchurch and McMurdo appreciate the opportunity for a little bit of vertical action in their transit flight, or we will have dedicated flights. But the idea is to basically fly on the C-130s for at least 3 field seasons, taking orcas like transect measurements and enabling a broader perspective on the time variation of atmospheric CO2 and its relationship to processes driving flux variability. With that, I'd just like to acknowledge my collaborators. Britt and I have worked very closely over the past several years to advance this analysis, and I think we've really benefited from. I'm certainly indebted to him. I've learned a lot from working with him. Catherine McCain and Colin Sweeney, both at NOAA, were really instrumental in sort of identifying some of these CO2 drawdown signals. And then I've listed a long list of collaborators here who've contributed to the interpretation and the writing, but I've left off a number of other people who contributed to collecting, the surface observations and providing support for the model development, et cetera. So this is an incomplete list. With that, I'm happy to take questions.
Well, thank you very much for this really nice seminar. Are there questions? I see a bunch of hands up. So let's start with Bruno Delille.
Okay, thank you very much for this pretty interesting talk. I have 2 questions. So you made the point that the land station and the inverse modeling cannot capture the outgassing of the Southern Ocean in winter, correct?
Well, I would say that, yeah, the inversion models have not converged on a consistent estimate of the fluxes.
Well, I mean, it's not even converging. Obviously, it's a source, while they are showing, most of them are showing a sink. So why that kind of, what is the rationale behind why this inverse modeling cannot see this outgassing of CO2 in winter?
Well, I think so. There's a variety of issues that I think fundamental is so. Let's just go back to the seasonal evolution of the fluxes, and I'll just put everything on the same. Okay, so here's that picture.
Yeah.
So basically, I mean, first of all, our flux estimates don't suggest strong outgassing in winter, but rather near neutral conditions, near neutral fluxes. The Socom floats and actually this pentagon or hexagon, whatever that is actually an inversion that incorporated Socom based PCO2 data. That's from Christian Grodenbeck, and so that does capture outgassing. But the majority of these inversions are using atmospheric observations collected at the surface station network. And the surface station network around Antarctica is not sufficiently dense. And the signals in atmospheric PCO2 or atmospheric CO2 concentrations are relatively small, right? So I showed you that the amplitude of variability in our amplitude of seasonal variability in our horizontal gradient metric is order 1/4 of a ppm. And that's a minuscule signal, right? So these are global models that are trying to develop a regional flux estimate in the context of much stronger constraints with much larger signals elsewhere in the world. And on top of that, the transport is highly uncertain. And so it's an under-constrained problem. And so that's why.
Okay, thank you. And I have another question. So you are using a Picaro, and so you have also the methane measurement. And
Yeah.
so what the methane measurements are saying to us in terms of outgassing or uptake of methane in the Southern Ocean, do you have some insights? Because, well, it's very poorly covered in the literature.
Yeah, so I actually looked at the methane data, and this is sort of the similar picture for methane versus CO2. So you should be familiar with these kind of transects here, where this is altitude, latitude for summer, for winter, and this is of methane. And so what we see for methane is basically these very, very almost, there's almost no variability in methane in the lower troposphere in the southern hemisphere. And here is basically the same metric. So now the delta theta metric computed for methane on all the flights. And there is seasonality, and a large component of that seasonality, I think, is attributable to oxidation variations that vary seasonally. But for reference, here's the magnitude of the CO2 in equivalent. So what I've done here is basically fit a line to the CO2 methane relationship in the upper troposphere to develop sort of a methane-based signature of northern hemisphere influenced air. And what this suggests is that there's no strong sources or sinks of methane in the high latitude southern hemisphere atmosphere. So, but other than the oxidation loss pathways, and that methane is transported from remote sources, predominantly in the northern hemisphere, aloft, and is mixed down. But that contributes very little that air contributes very little to contamination, our vertical gradient metric.
Okay, thank you very much.
Thanks. Should we move on to Alex?
Yeah, hi. Thanks very much for the interesting talk. So my question relates a little bit to this difference between the float-based estimate and your kind of integrated estimate from the aircraft campaigns. And one of the issues that we have for the ocean-based estimates is that as you were saying, that there is very little wintertime data in the shipboard data, and it's also very sparse in terms of spatial coverage, right? And well, one of the main thoughts from the Socom was that basically this difference in the spatial and temporal coverage leads to this difference that we see in the SOCUT only or Socom plus SOCUT derived estimates. So the question is really whether or not the same issue would apply to the aircraft campaigns. So because those were mainly summer, and the aircraft campaigns from winter really came from this one location, right, which is somewhere south of Australia or New Zealand, if I remember correctly. So wouldn't you be concerned that the same issue that we have with the ship and flow data also applies to the atmospheric data?
Yeah, that's a good question. So based on some analysis that I've done sort of in an ad hoc way, looking at the sort of timescales at which the atmosphere mixes, I'm pretty confident that the full zonal signal is quite well represented in aircraft observations like this, and specifically in the gradient as we've chosen, the vertical gradient as we've chosen to define it. So I think, early on in the talk, I showed gradients across the top of the boundary layer. And those are very responsive to regional scale influence, because that air is, has a relatively proximal regional footprint that is setting that gradient. But as you move up in the atmosphere, you're basically recipient of air that's being swept across the full zonal scale, and the signal is developing on timescales of a few weeks. And so over the period of interest, which are the seasonal evolution, I think the aircraft observations provide an extremely robust representation of that full zonal picture. I'd also just like to point out that the definition of this, what I've been calling an emergent constraint, includes transport integrations that were forced with the Socom derived fluxes themselves. Okay, and so the notion that there's some, these data basically illustrate exactly what you'd expect to see in the aircraft observations if the Socom fluxes were correct, which is to say, let's just look at this point. So TM5, this is a TM5 transport integration forced with the Socom only flux estimates. This suggests that for this particular campaign, which is the ATOM1, we would have expected to observe a positive vertical gradient of greater than about 0.2 ppm. But in fact, what the aircraft observed was something slightly negative of order minus 0.1, right? And so this is, and the linearity in this relationship is indicative of the sensitivity then of this metric to the variations in the fluxes of that order of magnitude. So I think there's certainly room to dig in deeper here, and I think it would be really interesting to sort of couple the boundary layer gradient sampling with regional fluxes, and then think more about how this stuff aggregates and how we can develop a consistent picture using observations on both sides of the interface. And I think there's a lot of exciting work to think about too. Yeah, that's a great question. Thanks.
Thanks.
Should we move on to Liddy?
Yeah, hi, thanks for the great talk. It was very interesting and very clear as well. I have a question about what's sort of relating to what Alex was brought up, but more from a spatial point of view. So it looked like most of the planes were obviously near the continents where people live. And well, I'm coming from more of an ocean perspective, but I know in the ocean there are sort of hotspots with different processes, and I know the atmosphere is better mixed, but I was wondering if that could matter in the inversion estimate, that the data is not so uniform in space as well, that there could be some processes from the open Pacific, for example, missed.
Yeah, possibly. I mean, I think you're referring to sort of the surface observations, as opposed to the aircraft, or both? I think
I meant that. Well, probably both actually. I was thinking of the aircraft observations, but yeah, probably both.
Yeah, well, let me just provide a few points of interest here. Each of these surface observing stations has a measurement protocol that has a clean air wind sector, right? And so they only collect data under certain atmospheric conditions with the objective of capturing sort of signals that are not dominated by local processes. That said, these stations on the East Antarctic margin, Shoya, Mawson, and Casey, tend to exhibit less summertime drawdown than the other stations, for instance, over on Drake Passage and in Palmer Station. It's tempting to sort of think about attributing some of that to the large scale structure of the variability here, where you have elevated CO2 on the continent, and the areas where you have really strong surface ocean productivity in summer have stronger depletion, and so indeed those stations tend to have a deeper drawdown and greater seasonality. So I think that there probably is some degree of that sort of structure in the observations at the surface. I think the key thing with the aircraft data, and I think there is the potential for aircraft data to exhibit some of that in the vertical gradient as well. But as you go up in the troposphere, the timescales over which that gradient develop are longer, and so that integration timescale provides a bit of buffering against that pure regional influence. So I think we could do a more formal analysis to really kind of understand what the appropriate observing system would be and where you can get the most representative sampling. I think my gut feeling is that it's actually it's much easier to do from aircraft, and that we could learn a tremendous amount about the carbon cycle locally, as well as resolve issues associated, for instance, with northern hemisphere and tropical carbon budgets, if we had a regular global scale aircraft observing system campaign that might manifest through the collaboration of an international collaboration, but something like 6 flights a year, pole to pole, where you're measuring these properties on repeat transects would be tremendous. And the other thing about that is that you can develop integral constraints because you're measuring the full troposphere, and so you're not subject to the same transport bias issues that the surface observations. The relative degree to which boundary layer ventilation occurs in a model is a major limitation for using those observations in the context of observing systems.
Yeah, thanks. And I'm guessing like normal commercial flights would be flying too high for that, right? Or
well, I think the EU has a commercial CO2 monitoring aircraft program, and I think the US is trying to develop one. And so there would certainly be valuable data, particularly in regions like the high latitude Arctic, where the number of profiles that have been collected to date is small, but you could get profiles collected on a very regular basis from aircraft coming into landings there. And so certainly for some applications, that would be a really relevant thing. I think for the Arctic methane questions, that could be transformative.
yeah, thanks.
Well, I see we're at the top of the hour, so I think we'll bring this to a close. Thank you very much, Matt, for a really wonderful talk and for lots of great discussion. And I think people are probably going to have more questions to follow up with in the future. This is really ripe for further exploration.
Sounds great. Thanks for the opportunity.
Yeah, thank you very much.
Yeah.
Bye.